Hello and welcome to Science with Mr. Weber. Today we will be investigating molar heat of combustion of two alcohols. So we've got ethanol and butanol. Now, molar heat of combustion is the amount of heat energy that is released when a mole of a chemical is combusted. So what this experiment does is we calculate the change in enthalpy of our reactants as they convert into products. And the way that we do this is through a process known as calorimetry. So in calorimetry, what we do is, because we can't directly measure the loss of energy of those compounds effectively, what we can do is measure their effect on their surroundings. And what we include as our surroundings here are just 50 mils of water. So the reason why that is useful is because we know a piece of information that's really useful. It's known as the specific heat capacity. So the specific heat capacity refers to the amount of energy required to increase the temperature of a unit of a compound by 1 degree Kelvin. Now, for water, in order to raise it by 1 degree Kelvin, that's the equivalent of adding 4.18 joules per gram of water. So that means that to raise 1 gram of water by 1 degree Kelvin, we need to provide it with 4.18 joules. Now, there is a calculation which we'll look at later on to actually work out what our molar heat of combustion is. But before we can do that, we actually need to record a few bits of information. Now, in order to perform this calculation, okay, we are going to need to know the initial temperature of the water. So it's sitting at 18.0 degrees Celsius, so we'll record that. Okay, it's also really important that we measure the mass of our fuel before and after. So let's have a go at weighing that. I'm just going to write that down. So 199.29 grams, and notice that I am weighing it with the lid on. Okay, so now that I've measured both the fuel source, the mass of the fuel source, and the quantity of water that I have, okay, we can, and we've also recorded the temperature, we can actually go ahead and start burning some of this fuel. Okay, so it doesn't actually matter how long we burn this fuel for. What is really important is that we are seeing the majority of that heat actually heating up that beaker of water. Okay, so that should be time. So we'll extinguish that. Now we do need to weigh the final mass of the ethanol. So we record our final temperature as 47.7 degrees Celsius, and our mass is 198.81. So let's have a go at repeating this for our other alcohol, butanol. Our final mass is 224.83 grams. Our final temperature is sitting at 57.0 degrees Celsius. We can go ahead and calculate our molar heats of combustion. So to calculate our molar heat of combustion, we need to use the following equation. So molar heat is equal to Q divided by N, and Q is the energy released by the fuel, and N is the number of moles of fuel burnt. Okay, so to calculate these, we need to use the following equations. So to find the number of moles of fuel burnt, we can just use the N equals the mass of fuel burnt divided by the molar mass of that actual compound. For Q, we can use Q is equal to mc delta T. Now, m is the mass of water used. C is a property or a number known as the specific heat capacity. And delta T is the change in temperature. So, change in temperature. And we've actually collected enough information from our experiment to go ahead and plug in numbers for both of these. Now, let's have a look at where we find that specific heat capacity number. So, what we need to do is we'll just take a look at our specific heat capacity of water down here. It's 4.18 times 10 to the 3 joules per kilogram per unit Kelvin. Now, I'm actually not a big fan of that number, simply because in chemistry we always use grams. So I'm just going to straight away convert that into 4.18 joules per gram per unit Kelvin. All I'm doing is dividing by 1,000 to find what it is for grams. So let's have a go at calculating our Q is equal to mc delta T for ethanol and butanol. So for ethanol, Q is going to be equal to 50 grams of water, which is what we use in the beaker, times 4.18. So just taking that straight from the data sheet, and we're going to multiply that by 29.7, which is the change in temperature that we observed. And we can calculate that, and what we end up with is 6,207.3 joules, but we actually want our final answer in kilojoules. So I'm going to go ahead and convert that now. So we're just going to divide that by 1,000. We end up with our Q as being 6.2073 kilojoules. Okay, now let's have a go at doing the same for our butanol. Okay, so for butanol, same process. Q is equal to 50 grams of water multiplied by 4.18 times our change in temperature, which in this case was 38.4 Kelvin, and we end up with a Q of 8.0256. So I did divide by 1,000 there, and that is in kilojoules. Okay, now that we've got our Q's, we can go ahead and work out what N is for both of these. We'll write our equation. It's equal to mass of sample divided by molar mass of our compound. So let's have a go at calculating number of moles of ethanol. So we have N is equal to the mass of sample is 0.48 grams, and the structure of ethanol looks like this. Okay, so we've got a couple of carbons, hydrogens, and an oxygen. We use the periodic table and we work out that the molar mass is 46.068, and that means N ends up being roughly 0.0104. We won't calculate that number fully just yet. I'm going to keep it in my calculator, and we'll have a go at calculating the number of moles of butanol, which is going to be equal to, we've also got 0.48 here as well, grams burnt divided by the molar mass. Now, butanol, similar to ethanol, but we have 2 extra carbons and 4 extra hydrogens. Okay, so again, use our periodic table, work this out, and we end up with 74.12 as our molar mass, and that gives us N as 0.0064 moles. Great. So let's go ahead and try combining these numbers. So that's N. Q for ethanol was 6.2073, and our Q for butanol was 8.0256, and the formula we need to use here is that one we looked at the start. So molar heat is equal to Q divided by N. So we'll plug this in. So Q over N for this is the same as 6.2073 divided by 0.0104. I'll just use my calculator here to give me a final number of 597 kilojoules per mole for ethanol. And for my butanol, I've got 8.0256 divided by 0.0064, which gives me a final number of 1,240 kilojoules per mole. Now, let's have a look at these numbers. So we expected that butanol would have a higher molar heat of combustion, which is what we can observe here, which is really nice. Now, the reason why butanol has a higher molar heat of combustion is that we have more carbons, more hydrogens, and therefore more bonds per mole in comparison with the ethanol, and all of those are going to take part in that combustion reaction with oxygen. So we end up with more material to burn per mole, and as a result we do expect it to be higher, and that is what we have observed here, which is good to see. But when I go ahead and compare my numbers with my SI data book's published values, we actually find that we are a little off. For ethanol, the published value is 1,367 kilojoules per mole. And for butanol, the published value was 2,676 kilojoules per mole. Alright, so what we can see there is that actually we really weren't very effective in our experiment. And the big thing is that we've lost a lot of that heat. Okay, we've lost a lot of the heat that was generated by our flame. Now, it was effective in showing the difference between our ethanol and our butanol, but in terms of trying to get these actual values, we're actually really far off. That's because we're losing so much heat to surroundings which isn't being detected. So it's about being able to detect all of that heat that's being released. If we had a better system that was able to measure all of that heat that was being released by the reaction, then we would be much closer to these published values. Alright, that concludes our experiment for today. Thanks for watching.